children, welcome to today's lesson, Potential and Kinetic Energy. Before going further, first let me share the learning objectives.
On completion of this topic, learners will be able to define work, define energy, define and discuss kinetic energy and potential energy, discuss gravitational potential energy, discuss conservation of energy, discuss potential energy of a spring.
ਵਿਦਿਆਰਥੀਓ, ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਵਿੱਚ ਅਸੀਂ ਕਾਂਸਟੈਂਟ ਫੋਰਸ ਦੁਆਰਾ ਕੀਤੇ ਗਏ ਕਾਰਜ ਦੀ ਵਿਆਖਿਆ ਕਰਾਂਗੇ ਅਤੇ ਨਾਲ ਹੀ ਅਸੀਂ ਪੋਟੈਂਸ਼ੀਅਲ ਅਤੇ ਕਾਈਨੈਟਿਕ ਐਨਰਜੀ ਬਾਰੇ ਵੀ ਜਾਣਾਂਗੇ. The meaning of the word work is quite different in the common language and in physics. Let us see how the work is defined in the terms of physics. Work is said to be done if force acting on a body is able to actually move it through some distance in the direction of the force. For understanding this definition,
consider an object lying on the table. Let a force F is applied on the object such that applied force is in the direction of motion of the object. Due to applying force, there is a displacement S in the position of the object. Therefore, work done W by the applying force is the product of force applied and the displacement covered.
thus, the work done by the applying force is equal to force into displacement. As we have seen that work done is performed by applying some force which may be constant or variable. Firstly, let us see what happens when the applying force is constant. The work done by a constant force on an object is the product of the magnitude of the displacement and the component of the force parallel to the displacement. Thus, if vector F is the force applied and vector S is the displacement in the direction of the force, then work done is W is equal to F into S, where F and S are the magnitude of vector F and vector S respectively. Now, let us see what will be the work done when the applied constant force is inclined with some angle with respect to the direction of the motion of object.
ਮੰਨ ਲਓ ਕਿ ਇੱਕ ਟਰਾਲੀ ਰੱਸੇ ਨਾਲ ਬਣੀ ਹੋਈ ਹੈ. ਆਦਮੀ ਰੱਸੇ ਦੇ ਨਾਲ ਕੁਝ ਬਲ F ਲਾ ਕੇ ਖੱਤੀਜ ਦਿਸ਼ਾ ਵਿੱਚ ਇੱਕ ਐਂਗਲ ਥੀਟਾ ਬਣਾ ਕੇ ਰੱਸੇ ਨੂੰ ਖਿੱਚਣਾ ਸ਼ੁਰੂ ਕਰਦਾ ਹੈ. ਲਗਾਏ ਗਏ ਬਲ ਦੇ ਕਾਰਨ ਟਰਾਲੀ ਕੁਝ ਦੂਰੀ S ਤੈਅ ਕਰਦੀ ਹੈ. ਇੱਥੇ ਮੋਸ਼ਨ ਦੀ ਦਿਸ਼ਾ ਹੌਰੀਜ਼ੌਂਟਲ ਦੇ ਪੈਰੇਲਲ ਹੈ. ਦੂਜੇ ਸ਼ਬਦਾਂ ਵਿੱਚ ਹੋ ਰਿਹਾ ਮੋਸ਼ਨ ਲਗਾਏ ਗਏ ਬਲ ਦੀ ਦਿਸ਼ਾ ਦੇ ਉਲਟ ਹੈ. ਮੰਨ ਲਓ ਕਿ F1 ਲਗਾਏ ਗਏ ਬਲ F ਦਾ ਹੌਰੀਜ਼ੌਂਟਲ ਕੰਪੋਨੈਂਟ ਹੈ. ਇੱਥੇ ਕੀਤਾ ਗਿਆ ਕਾਰਜ ਟਰਾਲੀ ਦੇ ਡਿਸਪਲੇਸਮੈਂਟ ਅਤੇ ਇਸ ਉੱਤੇ ਲੱਗ ਰਹੇ ਬਲ F1 ਦਾ ਗੁਣਨਫਲ ਹੈ.
Here, the amount of work done can be found by firstly finding the resolved component of the applied force. Let vector Fx and vector Fy are the forces along and perpendicular to the direction of the displacement vector S respectively. Then, modulus of vector Fx is equal to the F cos theta and modulus of vector Fy is equal to F sin theta respectively. As the body moves in horizontal direction only, therefore, work done by horizontal component of force is W equal to modulus of vector Fx into modulus of S, which is equal to F cos theta into S, or W is equal to Fs cos theta. Let this be equation 1. Now, when the motion of the object take place in the direction of the force applied, then theta is equal to 0 degree, which implies the work done is W is equal to Fs cos 0 degree, which is equal to Fs. Thus, we conclude that equation 1 can be used to obtain work done by a force in all the cases, in other words, when force may act or may not act in the direction of displacement. Thus, as F and S are vectors, then equation 1 may be written as W is equal to vector F dot vector S. Hence, work done by a force may be measured as the dot product of the force applied and the displacement caused by the force. As work done is dot product of the vectors, hence work is a scalar quantity. Now, if force vector F and displacement vector S are orthogonal to each other, then the angle between them is theta is equal to 90 degree, which implies the work done is W is equal to Fs cos 90 degree, which is equal to 0. Therefore, if a body moves in a direction perpendicular to that in which the force acts, the force does no work. Students, now let us see the unit and dimension of work done by an agent. The SI unit of work done is joule and denoted by J. The dimensional formula of work is m1L2 T minus 2. Let us now turn to the next topic, energy. Energy is the capability to do work. So, the energy is measured in joule in SI and erg in CGS system. Its dimensional formula is m1L to T minus 2. Let us see what is kinetic energy. The energy possessed by a body by virtue of its motion is called kinetic energy. Now, let us see some example of kinetic energy.
ਹਵਾ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਦੀ ਵਰਤੋਂ ਵਿੰਡ ਮਿਲਸ ਚਲਾਉਣ ਲਈ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਚਲਦੇ ਪਾਣੀ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਦੀ ਵਰਤੋਂ ਪਣ ਮਿਲਾਂ ਨੂੰ ਚਲਾਉਣ ਲਈ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਹਥੌੜੀ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਦੀ ਵਰਤੋਂ ਲੱਕੜ ਵਿੱਚ ਕਿੱਲ ਗੱਡਣ ਲਈ ਕੀਤੀ ਜਾਂਦੀ ਹੈ। ਬੰਦੂਕ ਵਿੱਚੋਂ ਨਿਕਲੀ ਹੋਈ ਗੋਲੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਦੀ ਵਰਤੋਂ ਕਰਕੇ ਨਿਸ਼ਾਨੇ ਨੂੰ ਪਾਰ ਕਰ ਜਾਂਦੀ ਹੈ।
Now, let us see how the kinetic energy of an object is measured. The kinetic energy of a body of mass m moving with velocity v can be found in two ways. First, by calculating the amount of work done by the moving body against the external force before it comes to rest, and second, by calculating the amount of work required to set the body into motion with the velocity v from its state of rest. Let us calculate the kinetic energy of a body by using the second method. For this,
consider a body of mass m initially at rest and suppose it starts moving with the initial velocity u. Suppose that a constant force F is applied on the body till its final velocity becomes v along the direction of force. Let S be the displacement of the body during this time.
Then, work done by the force W is equal to vector F dot vector S, which is equal to F into S as equation 1. If vector A is acceleration produced in the motion of body, then according to Newton's second law of motion, vector F is equal to m into vector A. As vector A is along the direction of F, then the vector condition of vector f and vector a may be omitted and we may simply use their magnitudes. Therefore, the equation 1 becomes W is equal to m into a into s, since the velocity displacement relation is v square minus u square is equal to 2 into a into s. If the body is starting from rest, then its initial velocity becomes 0, means that u is equal to 0, which implies v square equal to 2 into a into s, which implies the acceleration of the moving object as equal to v square by 2s. This implies the work done W equal to m into v square by 2s into s, which is equal to half mv square. As this much amount of work done on the body of mass m will set the body moving with velocity v from its state of rest. It is equal to kinetic energy of the body. Therefore, kinetic energy is equal to half mv square. From the formula of kinetic energy, we conclude that the faster the body moves, the more kinetic energy is produced in the body, and the greater the mass of an object, the more kinetic energy there will be. Let us now turn to the next topic, work energy theorem. Work energy theorem states that work done by a force acting on a body is equal to the change produced in the kinetic energy of the body. Suppose that a body initially at rest and the force vector F is applied on the body, displace it through vector ds along the direction of the force, that is, angle between vector F and vector ds is 0 degree. Then the small work done is dw is equal to vector F dot vector ds, which is equal to F into ds cos 0 degree, which is equal to F into ds. According to Newton's second law of motion, force F is equal to m into a. Here, a is acceleration produced in the direction of force. Thus, we have the small work done is dw equal to m into a into ds. Since acceleration of the body moving with the velocity v is a equal to dv by dt, which implies the work done dw is equal to m into dv by dt into ds, or dw is equal to m into ds by dt into dv, which is equal to m into v into dv. Therefore, work done by the force on the body in order to increase its velocity from u to v is given by w is equal to integration of capital M v dv over the limit u to v is equal to m into integration of v dv over the limit u to v. On simplification, we get w is equal to m into v square by 2 with lower limit u and upper limit v, which is equal to m into whole v square by 2 minus u square by 2, which is equal to half mv square minus half mu square. Hence, work done on a body by a force is equal to change in its kinetic energy. Now, let us see what is power. The time rate of doing work is called power. If an agent performs the work W in time t, then average power is P AV is equal to W by t. Since work W and time t are scalar quantities, therefore, their ratio power is also a scalar quantity. The power of an agent during a time interval may not be constant, and in such a case, the power of an agent at any instant termed as instantaneous power. Thus, the instantaneous power of an agent is defined as the limiting value of the average power of an agent in a small time interval when the time interval approaches 0. Now, if delta W is work done in a small interval delta T, then instantaneous power is defined as P is equal to limit delta T tends to 0 delta W by delta T, which is equal to dW by dt. Since the work done for a small distance ds is given by dW is equal to vector f dot vector ds, which implies P equal to vector f dot d vector s by dt. Since instantaneous velocity of the particle is vector v equal to d vector s by dt, this implies P equal to vector f dot vector v, which is equal to fv cos theta. The dimensional formula of power is m1L to T minus 3. The absolute unit of power in SI is watt, denoted by W. Now, let us see what is potential energy. Potential energy is the energy possessed by a body by virtue of its position or configuration. The potential energy of a system may be defined as the amount of work done in bringing the bodies constituting the system to their present locations after having been removed to position infinite distance apart. There are different types of potential energy such as gravitational potential energy, electrostatic potential energy, and elastic potential energy. In this lesson, we have to concentrate on gravitational potential energy. So, let us see what gravitational potential energy is.
Consider that a body of mass m is lying at point A on the surface of Earth. If g is acceleration due to gravity on the surface of Earth, it will be attracted towards the center of the Earth with a force mg equal to the weight of the body. In order to move the body up from point A to B with zero acceleration, a force equal to mg has to be applied on the body in upward direction.
इस करके जे बॉडी ਹਾਈਟ h ਰਾਹੀਂ ਮੂਵ ਕਰਦੀ ਹੈ ਤਾਂ ਕੀਤਾ ਗਿਆ ਕਾਰਜ W ਬਲ ਅਤੇ ਦੂਰੀ ਦੇ ਗੁਣਨਫਲ ਦੇ ਬਰਾਬਰ ਹੁੰਦਾ ਹੈ ਜੋ ਕਿ mgh ਦੇ ਬਰਾਬਰ ਹੈ। ਇਹ ਕੀਤਾ ਗਿਆ ਕਾਰਜ ਜੋ ਕਿ ਬॉडी ਅੰਦਰ ਜਮ੍ਹਾਂ ਹੋ ਗਿਆ ਹੈ ਪੁਆਇੰਟ B ਤੇ ਇਸ ਦੀ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਪੋਟੈਂਸ਼ੀਅਲ એનર્ਜੀ ਹੈ। ਇਸ ਲਈ ਪੁਆਇੰਟ A ਤੋਂ ਪੁਆਇੰਟ B तक पहुँचण लई पोटेंशियल एनर्जी mgh भी बॉडी दी ग्रेविटेशनल पोटेंशियल एनर्जी विच तब्दीली है। उधर mgh पॉइंट B ते बॉडी दी पोटेंशियल एनर्जी नू दर्शाउंदी है। जे इस दी पोटेंशियल एनर्जी नू धरती दी सतह ते पोटेंशियल एनर्जी दे जीरो लैवल ते लिया जावे। Students, now we are going to learn the conservation of mechanical energy for this.
Consider initially the body in the position of rest, say at point A at the height of h unit. Suppose the body falls through a height x and reaches the point B. its height above the ground will become h minus x. Let v be the velocity of the body at the point B. When the body finally reaches point C on the ground, its height above the ground is obviously 0. Let v be velocity acquired by the body on reaching the ground.
Since at point A, the body is at rest means that its initial velocity is 0. Therefore, the kinetic energy of the body at A is 0, while the potential energy of the body is equal to mgh. Therefore, total mechanical energy at the point A is W net is equal to kinetic energy plus potential energy, which is equal to 0 plus mgh, which is equal to mgh. Since the body reaches the point B from rest with the velocity v, it has covered the distance x unit from above. As the velocity displacement relation is v square minus u square is equal to 2 into a into s, this implies v square minus 0 square is equal to 2 into g into x. On simplification, we get v square is equal to 2gx. Since the kinetic energy of the body is kinetic energy is equal to 1 by 2 into m into v square. Thus, we have kinetic energy is equal to 1 by 2 into m into 2gx, which is equal to mgx. As the body, when reaches the point B, it has covered the distance h minus x above the ground. Therefore, potential energy of the body at B is potential energy is equal to m into g into whole h minus x. Therefore, total mechanical energy at the point B is W net is equal to mgx plus mg into whole h minus x, which is equal to mgh. When the body finally reaches point C on the ground, its height above the ground is obviously 0. Let v be velocity acquired by the body on reaching the ground. Thus, we have v square minus 0 square is equal to 2 into g into h. This implies v square is equal to 2gh. Therefore, the kinetic energy of the body is kinetic energy equal to 1 by 2 into m into v square, which is equal to 1 by 2 into m into 2gh, which is equal to mgh. As the body, when reaches the point C, its potential energy is equal to 0. Therefore, total mechanical energy at the point C is W net is equal to mgh plus 0, which is equal to mgh. Hence, we find that for a freely falling body, the sum of the kinetic and potential energies always remains the same. As the body falls, its potential energy decreases, but at the same time, its kinetic energy increases by an equal amount. आओ ਹੁਣ स्प्रिंग ਦੀ ਪੋਟੈਂਸ਼ੀਅਲ એનર્ਜੀ ਦੇ ਵਿਸ਼ੇ ਵੱਲ ਮੁੜੀਏ। ਇਲਾਸਟਿਕ ਪੋਟੈਂਸ਼ੀਅਲ એનર્ਜੀ ਉਹ ਪੋਟੈਂਸ਼ੀਅਲ એનર્ਜੀ ਹੈ ਜੋ ਕਿ ਇਲਾਸਟਿਕ ਆਬਜੈਕਟ ਜਿਵੇਂ ਕਿ ਖਿੱਚੇ ਜਾਣ ਵਾਲੇ ਸਪਰਿੰਗ ਦੇ ਡੀਫਾਰਮੇਸ਼ਨ ਦਾ ਨਤੀਜਾ ਹੈ। ਇਹ ਸਪਰਿੰਗ ਨੂੰ ਖਿੱਚਣ ਲਈ ਕੀਤੇ ਗਏ ਕਾਰਜ ਦੇ ਬਰਾਬਰ ਹੈ ਜੋ ਕਿ ਸਪਰਿੰਗ ਦੇ ਕਾਂਸਟੈਂਟ k ਅਤੇ ਨਾਲ ਹੀ ਸਪਰਿੰਗ ਦੇ ਸਟ੍ਰੈਚਡ ਡਿਸਟੈਂਸ ਤੇ ਨਿਰਭਰ ਕਰਦਾ ਹੈ। ਇਸ ਕਰਕੇ स्प्रिंग दी पोटेंशियल एनर्जी स्प्रिंग विच इकट्ठी होई एनर्जी है जो कि कंप्रैस ਜਾਂ स्ट्रैच ਕੀਤੀ ਗਈ ਹੈ। ਜਦੋਂ स्प्रिंग अपनी आम हालत ਵਿੱਚ ਹੁੰਦਾ ਹੈ ਤਾਂ ਇਸ ਦੀ ਕੋਈ पोटेंशियल एनर्जी नहीं ਹੁੰਦੀ। ਹੁਣ ਅਸੀਂ स्प्रिंग ਦੀ पोटेंशियल एनर्जी ਲਈ ਇੱਕ मैथमेटिकल एक्सप्रेशन डिराइव ਕਰਨ ਜਾ ਰਹੇ ਹਾਂ। आओ ਵੇਖੀਏ।
Consider a light, perfectly elastic spring attached at one end to a rigid support at the point O, while the other end attached to a block of mass m. When the block is pulled to the point A from its equilibrium position C through a distance CA equal to L, then due to elasticity, restoring force is set up in the spring. Due to this restoring force, it returns to the equilibrium position C. Due to inertia, it overshoots the position C and moves up to the point B and so on.
Here, we are going to determine the potential energy of the mass m when the spring is pulled from the mean position C up to a point P such that Cp is equal to x. As we know that according to Hooke's law, F is directly proportional to extension in wire, or F is directly proportional to x, or F is equal to minus k into x. Here, k is spring constant. Also, negative sign shows that restoring force acts in the opposite direction of the increase of the displacement. Suppose that the block is further displaced through an infinitesimally small distance pq is equal to dx. For this small displacement, the restoring remains unchanged. The small work done in increasing the length of the spring by dx is dw equal to f into dx, which is equal to kx into dx. The work done in increasing the length of the spring by an amount x can be obtained by integrating the given expression between the limits x is equal to 0 to x is equal to x. Thus, the work done w equal to integration of kx into dx with lower limits 0 and upper limit x, which is equal to k into whole x square by 2 with lower limits 0 and upper limit x, which is equal to k into whole x square by 2 minus 0, which is equal to 1 by 2 into k into x square. This work done is stored as potential energy in the system at the point P. The potential energy of the system when the block is pulled up to the point A, that is when x is equal to L, then the potential energy of the system at the point A is W is equal to 1 by 2 into k into L square. Let us now summarize what we have learned so far. Work is said to be done if force acting on a body is able to actually move it through some distance in the direction of the force. Work energy theorem states that work done by a force acting on a body is equal to the change produced in the kinetic energy of the body. Potential energy is the energy possessed by a body by virtue of its position or configuration. So, now we come to the end of today's topic. Here is a test for you. Question: what should be the angle between force and displacement so that no work is done? And the answer is, the angle between force and displacement should be 90 degrees so as no work is done. Question: a milkman carrying a can walking on a road with uniform velocity. What is the work done by him? And the answer is, the work done by the milkman is 0. So, with this, we come to the end of today's class. I hope you enjoyed the lesson as much as I did. Looking forward to the next class with yet another interesting topic. Until then, goodbye.